All right, greetings everybody from Hannover Messe 2026. We're here with Matthias from Siemens. How you doing, Matthias?
I'm doing great. Thanks, Lucian, for having me here. So nice to talk to you today.
So today we're talking about software-defined system inside the tools and the transition. So Matthias, technology is one thing. Getting teams to adopting is yet another one. From your conversation with customers, what's the biggest mindset shift that they have to make before they adopt this technology?
I think when you talk about mindset shifts in terms of approaching a software-defined system, you need to start by asking the question of what does it get you as a customer? So where are the pain points in your day-to-day life? And the mindset that needs to shift is to think of a manufacturing site and automation task, not only as I wire some hardware pieces together, put some software on top, put some logic in, and then let it run and sit forever to run continuously. I need to have the constraints of I want to work with an adaptive production. I want to be more developer orientation, have more developer operations for my engineering. So I want to continuously update my machine. I want to be more resilient. I want to shift how I approach engineering, for example, when I go from I copy my code, I adopt the code for every machine. I have a jungle of versions on my machines to a standardized, modularized version of my PLC code. And also, if I have the needs at my facilities to increase, decrease capacities of control, and even connect to other higher level systems or data systems and AI solutions on the shop floor.
Thank you, Matthias. Now, last year during the SPS, you've announced the virtual PLC versions, or at least a couple of them. Realistically, what is the number one reason a plant engineer still picks the physical one?
I wouldn't say picking a physical over a virtual one is a discussion that we need to take, because I think the beauty of what we do is we offer both. So at the end, the S7-1500 virtual PLC and the normal PLC have the same components. They behave the same as a control layer. The thing changes in regards to what the customer needs from us. If they want to centralize their compute, for example, like some of our customers do, like, for example, Audi, where are here at us at the shop floor here or at the fair, and then you can reduce your invest on the compute side and scale through the virtual PLC. But also, if you want to combine data analytics and AI applications on the edge, it's beneficial to run a virtual PLC alongside it, because you already invested in that ecosystem. And then if you don't need that, it's perfectly fine if you stick to a hardware PLC. We as Siemens believe we need to offer both. We need to offer the flexibility for our customers, and this is why we do this.
So just to understand a little bit, the data analytics at the edge, are you doing that as a virtual because you get more power, or what would be the reason? Double click a little bit there.
I think there are two things to it. So we have our software infrastructure based on Industrial Edge. On this, we can run both the virtual PLC as a control stack or a control application, control runtime, or we can run data applications, for example, an industrial information hub, connectivity apps that we run to other systems. And so if you combine those on the same platform, run them on the same compute, you, of course, have less hardware investment because you don't need separate modules for everything. And that's where you get the power.
Got it. Thank you for that. Now, the engineering copilot for TIA Portal is currently in beta with pilot customers. It currently generates PLC code with natural language. Where does the engineer stay in the loop? And where there's a type of a test where Siemens says, well, AI should not be trusted here?
So actually, the IIoT engineering agent, as it's now called, is broadly released since Monday.
Okay.
So since 2 days ago, we have it now released broadly, so people can get it anywhere. That's maybe a good info. And I think where it comes down to is the aspect of using natural language helps us to reduce the complexity of some of the projects we have. It also forces us to work more and think more in terms of engineering projects, more modularized and standardized through libraries. Now, what the IIoT engineering agent is doing, the tool we're talking about right now, is that it can create these applications for you as a customer, but of course the human still accepts the project in the end loads it onto a PLC. But the beauty of it is, for example, if you get him a task to generate a function block, for example, it will generate the function block, it will consume it in TIA Portal, it will then compile it, and once it's compiled, it will check on errors, and if it has errors, it will run it again until it's finished, so it can consume and use all the tools in TIA Portal natively out of the box. So I would say the engineer becomes an architect of the system, and it's aided through an agentic AI system that helps him to generate the pieces needed to make his architecture or his building, his machines run.
We're here in Hall 27. There's other vendors, right? There's Beckhoff, there's Rockwell here, there's Phoenix Content. Other halls may have Schneider, there's software-defined automation. Every major vendor at the show has some version of software-defined automation. What is the one thing the Siemens approach that you believe that no one else can match today?
I think we think of it more holistic. It's not just a virtual PLC. It's not just a unified runtime that runs on Edge, so on HMI. It's not just Edge applications or Edge as an infrastructure. It's not just the compute. It's not just the engineering being IT-like or more and more IT-like, more and more AI-driven. It's a complete holistic picture. So it's a combination of all those toolings coming together, and we see this as a complete holistic vision and view of a software-defined automation system view that we approach in the future, and this is where we're heading towards.
Thank you, Matthias. Now, if software-defined automation continues at a pace you're seeing with current customers, what does a typical manufacturing automation architecture actually looks like in, let's say, in a couple of years? Give us a realistic version, not the aspirational one.
So, from an architecture perspective, what we see, for example, in terms of smartphones, like this, for example, or in cars, is something we will see also in automation. So, for example, in cars, you have one central compute unit and you have zones defined,
Right.
that you have as actuators. For automation, it will be in a way that we still have drives, motors, IOs, basically periphery, and components, hardware components that still rely on physical and electrical needs to perform. Alongside that, we will have either central or decentralized compute, which is more generalized, because it can then run both AI applications as well as automation applications. And on top of that, we need to span a software layer that decouples this hardware from the software layer and from the applications themselves. And on top of that, we will see a split in regards to how the applications are used. We will have control, where we need the real time, where we need determinism, where we need safety, where we need to ensure that the policies we set in an era where AI defines how we do manufacturing at some point. We need to set the policies through the control layer, because that's our integration layer where we make the critical decisions on the shop floor. And then next to it, we will have AI applications deployed, maybe closed loop, maybe also analytics applications. We will have data gathering. We will have connectivity to further systems. And the more or the less dependent they are on real-time credibility, the more they are pushed towards clouds, the more they are dependent on, for example, inconsistent amount of compute needed, the more they will be pushed to the cloud. For example, if I do a recipe update, I will push it to the cloud because I don't need to do that in real time. I need to do this in batches over some time. But if I need to do an actuation point definition for a robot, I do this on the real-time compute.
Yeah. Matthias, thank you so much for the insight.